Assalamu alaikum. So, in today's lecture, we'll be covering up the topic of differentiation from Cambridge A levels, CIA A levels. Uh, Without further ado, we will be getting started. But before that, just a few concepts with the basics of coordinate geometry and polynomial equations. Let's say we have a straight line. Consider this graph. Now, let's say we have these few coordinates and we have a straight line. Let's say y equals to mx plus c. And let's consider here our m is given 1 and c is 0. That means what? It should pass through the origin. C means y-intercept, because when we place the value of x to be 0, that means the c is 0, and c0 means let's do it in this. So y equals to m times 0, because x is like in this axis. Let's consider at the point of x0, at which point the coordinate y lies. So if we say that it passes through the origin, that means what? At x equals to 0, y should also be equals to 0. That means y should also be equals to 0. That means 0 equals to m plus m into 0 plus c. So that means 0 equals to 0 plus c. That means what? C equals to 0. And c means the y-intercept. That means the straight line passes through the origin, as we have said. And m is given as what? 1. That means for every increase in the value, or for every increment in the value of x, the corresponding increase in the value of y is 1. Or we can say there is a constant, there's a constant increase which gradually increases, but that gradual increase is constant. It doesn't like accelerate, or the rate doesn't change. So it is, let's say, the rate of change of rate doesn't change. Only the rate changes, or only like the change of rate is constant. Let's not confuse. That means if c is 0 and m is 1, then the equation should look something like this. Y equals to 1x plus 0, or which we can simply write as y equals to x. That means at every value of x, we have equivalent value of our equal and same value of y. That means if x equals 1, y equals 1, that means this is the position. And when x equals to 2, y has a position of 2 as well, according to the equation. That means y should lie somewhere around here. And if we draw the straight line, then it should look something like this, isn't it? Okay. Now, we got to know the equation. We know the gradient. The gradient is what? The change in y over change in x. That means gradient is itself m. M means what? Del y over del x. Del y over del x means change in y2 minus y1 divided by x2 minus x1. That means the difference between 2 points. So in this scenario, let's consider these 2 points. This is the final position, or let's say one of the position, and this is another position. This is, let's say, this contains x2 and y2, and this is the coordinate which contains x1 and y1. Now, if we place this in the equation, what do we get? Let's calculate this. So m equals to y2 minus y1. Y2 is what? Here y2 is, we got to know from this point, it is 2, isn't it? So 2 minus y1 is what? We have y1 over here. Because like y1 is over here, not here, because we write the coordinates in that way, like x and y in terms of this, like in this way we write the coordinates, isn't it? That's why the y1 or the x1 and y1 is over here, and the x2 and y2 are over there. Now you can also consider them in the reverse way, like you can also consider this as the x2 and y2 and this as the x1 and y1. It does not have any like convention to be followed. I just try to follow, let's say, the rightmost value, like towards the rightmost value, which lies over here towards the right of the graph, that to be the y2 and x2, and towards the left I considered it to be x1 and y1. Now the y2 is 2 and y1 is what? It is 0, because at that point, at this point, y1 is 0, divided by x2 is what at this point? That's also 2, and x1 is here at this point, that is 0. That means we are left with the values 2 over 2, which gives us the value of 1. Now see, m is equals to 1, which we previously mentioned, and we know from this equation as well that this graph or this curve has a gradient of what? 1. That means what? By looking at the gradient, we know it has a constant gradient, and we know that for each level, I mean, for each step of increase in x, we got the same amount of increase in the value of y. And gradient means what? Rise over run. Rise means this is the rise value, like this is the rising value, rising part, which rises above. Over run, that means this is the runway, like that's the run. So this is rise over run. Okay, so that's the term we define about like the gradient. Now, if let's say we considered another graph which has, let's say, some sort of this type of equation. Okay, this table. And let's say we also mark this axis equally 1, 2, 3, 4. 1, 2, 3, 3, and 4. Now, like for us, curvature, like as I was mentioning, for the previous curve, which was a straight line, this gradient remained constant throughout the like entire graph. Like if we consider, let's say, towards negative infinity, that means like it goes towards, let's say, billion, trillion to the value of negative x. And if you consider the values towards the positive infinity, like this gradient, it remains constant. At whichever point we calculate for that straight line, it was constant at 1. Okay. For this one, for this type of curve, which has like a curvature, it does not have, let's say, a very straight line. This type of curve does not have a constant gradient. It changes over time. How do we calculate gradient? In physics or in chemistry, you have probably used it, or in O-level mathematics, in mathematics D, you have calculated more or less the gradient, or used to calculate, which is we try to find a fixed point, which they tend to say what, like usually when people ask, or when it is asked in the question, find the value of the gradient of this curve at this point. This curve has, let's say, an equation of y equals to, let's say, x squared plus 0. So yeah, this is the equation simply, y equals to x squared. This is actually the equation of this curve. So we are just considering the domain of where x is greater than or equals to 0. Okay. Now, when they're saying to find the value of the gradient at this point, what do we do usually? We try to sort of like take a ruler, take a scale, and try to find the nearest, like as much as possible, as much close as much possible towards that point. We try to like eliminate any sort of like distances from this point. So we will be like focusing so that here we have very less distance, and this point is very at a very negligible distance, or we will be considering like placing the ruler just over that point, the edge of the ruler at that point, and hence we'll be calculating, or we'll be taking 2 points from this ruler anywhere from this ruler, and we will be trying to find, let's say, we'll be marking, at first we'll be marking 2 points. Over here, if we mark which point it lies, let's take this a bit further. Let's say it goes over here at 3, and we'll be trying to find what is this value at the value of 3, what is the corresponding value of y from this graph. We'll be seeing, let's say this is somewhere 3.1. So here we have coordinates of 3 and 3.1. Okay. And the other way, let's say we have let's say here 1. Let's consider, okay, let's do one thing. Yeah, let's consider this point, which is the point 0. At the point position 0, let's say this is the position of x to be 0. X over here 12, this entire line x is 0, but x over here is 1, x2, x3, x4. So that's how it goes. So over there, this point is x0. At the point of x0, what is the value of y? So if we extend this axis and we sort of assume if that's the value of -1 of y, then it lies somewhere below -0.5. So let's consider this as -0.4. That means we have a value of 0 and -0.4. These are the values of the y. Okay. Now, if that's the case, if we are asked to find the gradient at the point x equals to 1, we will be simply trying to find the gradient using the equation y2 minus y1 divided by x2 minus x1, where y2, let's say over here, is 3.1 minus y1 is minus 0.4. Remember, if your value of y is minus, then you should consider that in a bracket, and this negative, this y2 minus y1 itself, this negative value is the sign of the formula. So we are not to change the sign deliberately. You will keep that sign, as well as if the coordinate itself has a negative sign, you will also consider that. And when we break the brackets, if it is negative and negative, that will get multiplied and become positive. Similarly, we have x2 as 3 over here and x1 as 0. So breaking the brackets, we get negative gets multiplied with negative and becomes positive. So that means positive 0.4 divided by 3, we have 3.5 over 3, which should give us an equation or a gradient near to 1.1 something. Or let's give me a second. Let me calculate that. Opening up the calculator. 3.5 divided by 3. It gives us a value of 1.16667. 1.16667. So that's the gradient. Okay. Now, talking about this, it gives us a very, let's say, sort of approximate values. Or like using the ruler, we are not getting as accurate or as exact value as possible. So there we get to introduce with the terms differentiation. I know this is not exactly how it works, but this so far explains the easiest concept, that how it works. It might sound confusing now, but let's do a couple of things so that we understand what is the basis. Now, the topic differentiation is simply the process of finding the rate at which the function changes. Now the function means this is a function that is another function. We just saw this two functions just previously a few moments ago. So differentiation means simply the rate at which the function changes. That means simply the gradient. That's the term, rate. Because if we introduce a m here, m means gradient, and M in every case is what? M equals to, like, if you make M the subject, that means y over x. Simply y over x means what? If we consider, let's say over here, time, like on the x-axis, time as, let's say, hour, and on the y-axis, distance in kilometers, that means what? Here, this is y, this is x actually, like y-axis and x-axis. And if we divide y-axis by x-axis, what do we get? Distance over time, which means kilometer per hour. That means what? This is the, like, this is the unit for what? Speed or velocity. And that means what? It is actually a rate. We're calculating a rate here. So that's the rate of the speed. Now, this means the rate at which the function changes, or the rate at which the speed changes, or the distance changes, the rate at which we're covering the distance, rate at which we're covering up a certain speed. It's that sort of thing. Rate of change of velocity means acceleration, and rate of change of distance means, like, rate of change of distance means the rate at which the distance changes. That means with per unit time, how the distance change is changing. Here, according to this unit, this means, let's say if we have 10 kilometers per hour, that means in every hour we are covering up 10 kilometers. That means we are changing the rate of distance. That means, we are changing the distance at a rate of 1 hour. Like every hour we are covering up 10 kilometers of distance. That is a simple rate. Like, at that rate, we are covering up the distances. So that's what the term differentiation means. Now, if we try to get to the simplest terms, in other words, it tells us how quickly a function is changing at a given point. As we saw in that curve, this is a point, and where we try to find the gradient by plotting 2 points using a ruler, and we try to find the gradient. That means at this particular point, how the function changed. If we would have considered, let's say this was a straight line, at that specific moment, how this gradient was changing of the straight line. Okay, it is easier for us always to find the gradient of the straight line. That's why whenever we try to find the gradient of any curve or anything, we try to observe, if, like, we try to place a ruler there, and we try to observe if it was a straight line, how would it have changed, or how the rate would have changed. Based on that assumption, like if it was a straight line, how would the increase or how would the decrease be happening, we try to assume the gradient. Okay, so based on that, differentiation has certain formulas, or the differentiation terms actually came, and after that we tend to have different forms of differentiation. Some are very natural differentiation, like they're very, like, simple, straight, go ahead differentiation, and some are having some complex sort of formula. The only thing, like, about the coordinate geometry polynomials is the thing we just saw, like just a moment ago. That is the basis of the differentiation, and based on that, every other sort of differentiation is going to work. Whatever complexity you encounter, the fundamentals are those. Like, that's how it works, or how differentiation at the basement works. Now, coming back to our form, let's say we have this equation y equals to x squared. Okay, according to differentiation, we write the term differentiation, or we try to find the rate of change of this function as dy by dx. Now, dy by dx means, like, this has a simplest, what should I say, synonymity or close relation, or it's sort of, it's not equal, but it is sort of approximately equal to the term del y by del x. Okay. Now, when this del, that change over here, what did we do? We tried to find, like, this distance or this change value, like the change values, isn't it? This del y, and this is the del x. Now we have a sort of difference in the value of x and y, isn't it? We try to find the change in the value of y over the change in the value of x, isn't it? Now, when this change in value becomes so less, like when we try to minimize them, let's say if this is the point, let's say 4, and this is the point which is like y is 3, 4 minus 3 is 1, isn't it? Now, we try to reduce this distance. So let's say we consider it 4.5, and here we have, let's say, 3.4. Sorry, here we have not 4.5, sorry, it should be less than 4. So 3.5, and here we have this 3.4, and that is equal to 0.1. And we try to reduce it further. Let's say now 3.54, 3.4, 0.00005 minus 3.400000, like that equals to 0.00005. Like, I hope you're getting it, that the further we like reduce this distance, the further we minimize it, that tends to become close to, like, that tends to become equal to 0. Remember, it's not 0, but tends to become 0. Limitation, it sort of gauge that approximation of becoming 0, but it is not 0. When we get to that point, then we can sort of, or we can say, we can find the gradient or the rate of change at that specific moment. Because consider, just focus on the term, like focus on the concept. Usually, like previously we mentioned, of that, like the curve, we couldn't find actually a very specific point of that curve where the gradient would have, like, we could have found the gradient. It's like, did we do actually? What we did was, we used the ruler and found the 2 points, isn't it? And that 2 point had certain distance to be covered, isn't it? Like, it has a certain variation over here. This was the distance of, or the change in the value of y. This was the value of the change in value of x, isn't it? This was the change in value of the x. So del y and del x was sort of having some basement, sort of like was having some sort of distance to be covered. And when distance is minimized so much that we sort of get to that nearest point, or both the value of y and x is sort of closer to that point, we sort of get a very accurate, not exactly accurate, but approximately accurate value of the gradient. Thus, the term is represented as differentiation, or dy by dx. This formula then, del y by del x, tends to become dy by dx. If that's the case, the dy by dx of this formula, of this equation, is going to be 2 times x. Now, how does that happen, or how this takes place? Simply think it is like, it has a concept to be followed, or a formula, simple formula, which is, whenever, let's say, we have x to the power n, x to the power n, where n is the power of this x, the formula is going to be, when we find the differentiation dy by dx, it becomes, we have to bring the n to the front. That means n will be multiplied with this x, and the power is going to be reduced by 1. Okay, so n x to the power n minus 1. That's the formula of our differentiation. So if we just consider the previous example, x squared, let's implement this in this formula, we should get y equals to 2 times x to the power 2 minus 1. That gives us the value of 2 into x. Okay, now if we place the value of 1 in this equation, we should get y equals to 2 times 1 equals 2. Okay, so that means, sorry, this is not y, this is dy by dx. I'm very sorry, dy by dx. dy by dx, dy by dx. Yeah. So dy by dx here is 2. That means if we have this equation, or this curve of y equals to x squared, at the point of, let's say, x equals to 1, we should have a gradient of 2. But in our example where we use the ruler, let's say, like, since I drew it with a freehand rough sketch, we got a value of 1.1667. I know it was not close, or not very close to this value, but you got it, isn't it? Like if we would have drawn it to the like accuracy, exact like accuracy, we would have like we would have gotten a very much similar value to this one. It would have it might have been let's say 1.8 to 2.2, like close to this value. You can like simply try it by yourself and you would get a value, let's say closer to this value, a value of 2. So when we are getting the value of 2, we're getting this value of 2 when we are trying to minimize the effect of this change in value of x and y. So if let's say we were considering 2 points on this ruler, if we could have drawn a triangle over here, and in the triangle, these are the 2 points where we find the like, value of y2, x2 and y2, yx1 and y1. If we try to minimize this distance covered over here, these two distance, if we try to minimize them and bring it as close to the point, to that exact point as possible, let's say this was the value of x equals to 1, and we try to bring this change in value of x and change in value of y as close as possible and make it as much closer to the value of 0, then we can find the value of the differentiation dy by dx. Then we can differentiate them. So that is the concept of differentiation, and that is the concept like we are using differentiation, the equation or the formula differentiation, the concept differentiation, rather than a straight ruler to find the gradient. Because in the straight ruler, we sort of tend to get errors, like we get estimated values. In differentiation, we also tend to get differentiation like estimation value, but still, this value, it is like more than 90% accurate. And it also makes our life easier. Now, talking about some other examples, we have, let's say, y equals to f, the simple straight line equation. If we implement that formula over here, then y equals to, here we have a formula imaginary 1. So that means 1 is going to be like brought to the front, and we'll be having x to the power 1 minus 1, which gives us a value of 1 times x to the power 0. And don't think x to the power 0 means 1. Anything to the power 0 is equals to what? 1. Anything to the power 0 is equals to 1. Okay, so that means x to the power 0 is equals to 1. So 1 times 1 equals to 1. And remember, by looking at this equation, we can simply say this as a gradient of what? A gradient of 1. Okay, but like simply observing this, because we know at the front we should have a m, and if there is no m given, that means what? We have an imaginary 1 there. Because if we multiply anything with 1, that becomes that number. Like 1 times x is x, 1 times 0 is 0, 1 times 5 is 5, 1 times billion is billion. So that's how it works. Now, let's do some more examples, but before that, I want to show few of the crucial problems or crucial parts, which usually are sort of like the advanced concepts, like which are already derived, but we just need to know them. For example, y equals to sine x. Okay, sine is the curve which have a function like which we get the equation of this. This is the curve of the sine x, so it continues, and cos x is simply this. Okay, we'll get to know this type of function more in future, but for now, remember, if we differentiate sine x, then we get the value, or we get the term cos x. Okay, cos x. When we differentiate sine x, we get cos x. And when, let's say we have equation cos x, if we differentiate them or differentiate it, we get not sine x, we get negative sine x. Okay, so these are the this is the concept which you should remember. Then we have some other, you can take notes of them, because these are some of the most important terms. In question, you often get this sort of questions. So when you have sin x, just simply remember the differentiation of sin x is simply cos x, and the theoretical differentiation of cos x is negative sin x. Now, if you have then negative cos x, that means what? When we differentiate it, we at first consider the negative sign in front, okay? Just don't do anything with it. Differentiate cos x itself, okay? Dy by dx, we get negative sin x, okay? Now, after breaking the brackets, we get positive sin x, okay? That's how it works. That was the term for sin x. Now we'll be observing another function which is equals to e to the power x, which is another very common function. This is the e is the term exponent, so exponent to the power x, and whenever we differentiate this term exponent, we get, if this was an x, remember, if this is an x at the top, like the power is x, we differentiate it, we simply get e to the power x. It doesn't change, okay? It never changes. It never changes. That's what we need to remember. But if, let's say, we have y equals to e to the power 2 or any constant value, then the differentiation is simply what? We would consider this as a 0. This as a constant value. We would consider this as a constant, okay? Constant doesn't change. Constant remains constant. Because let's say we have a straight line y equals to 2x, okay? The gradient is what? We can observe from the equation the gradient was 2, but we can use the differentiation formula. The constant gets multiplied, okay? That constant does not change. The constant remains how it is. So here it is the coefficient or the constant value which won't change. We would simply apply the differentiation on this value x. So implementing the differentiation on this value x gives us x as a power of 1. So 1 times x to the power 1 minus 1. Simply we would get what? 2 times 1 into x to the power 0, y equals to 2 into 1 equals 2. That means what? Y equals to 2. That's the gradient. Similarly, if this is the constant value, we would simply don't do anything to that. But remember, here we have what? An imaginary x to the power 0. Why? Because remember, we can also represent, like, simply think e to the power 2 times 1 is what? E to the power 2. And we can represent this 1 as what? It's x to the power 0. Because we need an x. Because in order to calculate, we need that rate of change of y over rate of change of x, isn't it? So in order to get that x, we need what? In order to do differentiation with respect to x, we need what? We need x. So the simplest term is to reverse here. We know 1 is equivalent to x to the power 0, or anything to the power 0 is equal to 1. So we can also write it as e square times x to the power 0. Now, if we do the differentiation of this x to the power 0, what do we get? 0 times x to the power 0 minus 1, isn't it? And anything is multiplied with 0, we get what? Anything multiplied with 0 becomes 0. 0 times 1000 is 0. 0 times billion is 0. So anything you multiply with 0, it becomes 0. That means differentiation of any constant number is 0. Why? If you consider a straight line, just a simple straight line, which passes through parallel to the x-axis. So let's say here we have 2 points. Here we have 4, and here we have 1. And the value of y at this point is, let's say, y equals to 3. Okay. Over here it is y equals to 3. Over here also y equals to 3, because y is never changing. So if we want to find this gradient, if using the equation m equals to y2 minus y1 divided by x2 minus x1, we should get 3 minus 3, because here we have, okay, let me write the coordinates, 4, 3, and here we have 1, 3, isn't it? So y2 is 3, y1 is 3, so 3 minus 3 divided by x2 minus x1, which is 4 minus 1. And in the numerator, we get 0 divided by 3. Now, whatever it is in the denominator, it doesn't matter. If just simply we get a 0 in the numerator, or any number is multiplied with this value is 0, we get a value of what? 0. So that is the reason the differentiation of any constant value is what? 0. Okay, clear with this part? Now, Let's dive a bit further. Remember, for y equals to, let's say, ax square plus bx plus c, in this sort of equation, okay, we individually implement or apply the differentiation term. So if we are to find dy by dx of this whole term, we individually apply differentiation on this whole terms, like on this individual terms, okay? If these are like arithmetically combined, like I mean addition or subtraction is between them. So dbx by dx plus dc by dx. This is the like this is how we represent the differentiation function. Okay, so placing simply the function inside this means that we have to differentiate what is inside the bracket. So simply writing this, we get differentiating this ax square. What do we get? A is the constant, it remains constant, multiplied with this, the differentiation of this equation, like this term, x squared. It is what? X, 2x, isn't it? Because using that formula, plus differentiating this inner part becomes b times x. Like if we have a power of 1, that becomes what? Just simply 1. 1 times x to the power 0. You feel not so much comfortable with this term, we would like we can also write the like numerical values. Plus this is a constant, and we know constant times we have a imaginary 0 here, so 0 times x to the power -1 or 0 minus 1, so we get -1. And remember, we don't need to write anymore like d by dx, because this expression, this term, that means we have to differentiate this function. Once we differentiate it, we don't need to write this term here, but we have to write the final dy by dx over here. Dy by dx equals to, means what? 2ax, just rearranging the terms, plus bx plus 0, and we don't need to write that 0 anymore. Simply, this is our what? Differentiated function. Now, if we do an example, let's say we have a function of y equals to 3x to the power 4 minus 2x cubed plus 5x squared minus 7x plus 1. You can pause the video here and see, try to do it by yourself. I'll be doing it like simply. Dy by dx is going to be 3 is the constant times x to the power 4. If we differentiate this term, we get 4 times x to the power 4 minus 1 minus 2 is a constant times differentiating this inner, like that term of x, which is 3. I mean, the power comes in front times x to the power 3 minus 1. This power is going to be like placed in front. The initial power is going to be placed in front. Okay. Then we have plus 5, which is the constant, multiplied with the inner value of x, which is going to be like coming in front. So we will simply get 2 times x to the power 2 minus 1 minus 7 times 1, since this x has a value of 1, times x to the power 1 minus 1. Finally, we have 1 times x to the 0, since we have here x to the power 0 here. So 1 times 0 into x to the power 1, 0 minus 1. Finally, we get the value of what? 3 4 the 12, x cubed minus 6 x squared plus 10x minus 7, and we get a value of 0. So that is our differentiation value of that equation. Okay. The differentiated value of that equation is 12x cubed minus 6x squared plus 10x minus 7 plus 0.